So in this video, we'll do a couple of exercises from the linear DE section. And so here is an eigenvalue and an eigenvector. I'm pretending that those are coming from some matrix A here. So what I'd like to do is I'd like to form the solution. So form the solutions to x prime equals ax. Okay, now you'll remember that in the case of the complex numbers, we have to form e to the lambda t times v, which is a complex vector, and then break it apart into the real part and the imaginary part. And then these two pieces are the two pieces for our solution. Okay, so in this case we have e to the 1 plus 2i t times our vector. Right, so that's going to be e to the t times e to the 2it. I'll just go ahead and carry this along. And then remember that the e to the 2it is where our Euler's formula comes in. I'm going to just abbreviate this with a c and an s. So that's c of 2t plus I times s of 2t. So that's our cosine and sine. Minus I, 2 plus I. And then we just go through and multiply things out as usual. And I'm just, the e to the t is just coming along for the ride here. So then we get cosine for a real part. And then minus I times cosine. And then plus I times sine. So that's going to be part of this piece. And then minus I squared times sine, and minus I squared would give me a plus. Good. And then similarly for the bottom one, we would have 2 times cosine. I'll just abbreviate with 2c for now. And then if I keep going with my expansion here, I get I cosine. And then plus 2 times the sine. And then plus I times the plus I times I sine is going to give me I squared sine, so that's going to be minus sine. Does that make sense? I hope my abbreviations aren't too much for you, because these are, if I just rewrite this, that's 2 cosine 2t minus the sine of 2t. And then these just drop down. And so let me just go ahead and write down my solution now. So y of t, or x of t, I guess I'm calling it for my vector form, c1 e to the t times this is the real part now, cosine of 2t plus the sine of 2t, and then 2 cosine t, 2t minus the sine of 2t, plus c2, and then I've got my imaginary part. Now remember, the imaginary part does not have the I in it, right? So you were factoring the I out. It's minus cosine plus the sine, and cosine plus 2 times the sine. Good, and so there is the solution. By the way, what's the origin in this case? With that exponential function, you know that solutions are growing in size, and with the sine and cosine we know it's also rotating, so therefore this is a spiral source. Okay, there's a couple ways we could figure out if we're going clockwise or counterclockwise. The easiest way we had was going back to the matrix, so since we don't have the matrix in this one, I won't continue with that. Good, so this is the case where we have complex eigenvalues. Let's try one where we have a single double root. I'm going to pause while I write down the differential equation. Okay, so here's an example. We see that the trace is 0. The determinant is 0. And so we have lambda equals 0, 0. So we have the double zero eigenvalue. So on the Poincare diagram, you'll see uniform motion, And so sometimes that's confusing. Let's just go ahead and see if we can solve this and see what that uniform motion means. Okay, so if we go through and solve this, we get oh, where am I? I guess we don't need the eigenvalue vector, right? Because in our technique, we're given our x0, y0, right? And then we just determine w by taking our a minus lambda x0 plus by0, and then cx0 plus d minus lambda y0. So in this case, yeah, we'll just have our lambdas are both 0, and so this is just going to be x0 minus y0, and this one will also be x0 minus y0. Good, so this is our w. Okay, and so now we have our solution. X of t is equal to e to the 0t, which is 1 times x0 y0 plus t times x0 minus y0, x0 minus y0. Very good. All right. Yeah, so I think we can we figure out what this looks like? Where are the equilibrium solutions at? Well, remember, we have x prime is equal to x minus y, and actually when y prime is also x minus y. And so we see here that our equilibriums, our null lines, are where x equals y. And so along x equals y, both x prime and y prime are equal to 0. So these points are all fixed. Okay. And you see that in here, right? Because if x0 equals y0, that zeroes out the t, and you're just left with that. Very good. So now what happens if we're not there? So for example, if we're in this region of the plane, well, that means that, hang on one sec. Okay, so above here, y is bigger than x. So if we go back to our null plane analysis, right, that means that our x prime is going to be negative and our y prime is negative, meaning we're going to be going left and down or that direction. So these solutions are all going this way. Now there's no exponential function. These are, the derivative is constant here. So that's what we're meaning by uniform motion, is that the derivatives are all constant. And then for these down here, you see that in this case, the x is bigger than y, and so both x and y are going to be positive. So you're going to be going to the right and up, which means you're going to be moving in this direction. And again, the derivative in time is just constant, right? So good. And so that's a picture of uniform motion. So everything is moving. The speed is uniform, right? And then if you're on the line, it just means that your solution is constant. Good. So I just wanted to do one of those because it's kind of a weird example when you have a double zero. Very good. I think we've got time for one more. Let me pause and get it set up. Okay, so maybe we'll do a conversion problem for this last one. So suppose that x prime equals x plus y and y prime is equal to 4x plus y, and we want to convert to second order. The idea here is that we're going to solve the top equation for one of the variables, in this case y, so we'll take y equals x prime minus x, and then we substitute it into the second equation. So in place of y prime, we're going to have x prime minus x prime. Then we'll have 4x plus y, so I'm going to have the x prime minus x. And then we just simplify that. And so what do we get? Looks like we get x double prime minus 2x prime. If we bring that over, and then here we have a 3x, which we'll bring over. Good. All right. And so this is our second order differential equation. Whoops. Now, how would we convert y double prime? Oops, just got to the bottom of the page. Y double prime plus 2y y prime plus y cosine t equals 0 to a system of first order. Well, we let x1 be equal to y and x2 be equal to y prime. And then we find our differential equations, or our derivatives for x1 prime and x2 prime. Please put them in order. X prime, or x1 prime is y prime, which is x2. By the way, that's always going to be true. And x2 prime is y double prime, so I can just solve this equation for that. And so in place of the y and y prime, I'm going to put x1 and x2, so that's going to be minus 2 x1 x2, and then minus x1 cosine of t. Now, that's fine if you want to write it this way. You could introduce a third variable if you want. You don't have to, but we could let x3 be equal to t if you wanted to, and then make this x3, and then take x3 prime to be equal to 1. And so that is also that would also work. You don't have to introduce the x3 if you don't want to. That would just give you a system of two equations with a non-autonomous differential equation. But in this case, we have a system of autonomous differential equations, which is kind of nice. Good. All right. So those are our conversions back and forth.